Obtain the Fourier series representation for the function f of x equals pi x when x belongs to closed interval 0, 1 and f of x equals pi times 2 minus x when x belongs to closed interval 1, 2. We have the given function displays pi x as the output when input belongs to closed interval 0, 1. When the input values belongs to closed interval 1 to 2, we have the output displayed by the function as pi times 2 minus x. We have to deduce the relation 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus etc. equals pi square by 8. We have the general interval for f of x given by closed interval c comma c plus 12, and here the interval in which function has been defined is closed interval 0 to 2. Thus we have comparing c comma c plus 12 to closed interval 0 to 2, we have c equals 0 and c plus 12 equals 2, from which we have L equals 1. Thus we have the Fourier series representation for this given function given by f of x equals a naught by 2 plus summation n ranges from 1 to infinity a n cos pi n x by L plus b n sin pi n x by L, where L equals 1. A naught can be evaluated using the formula a naught equals 1 by L integral 0 to 1 f of x dx plus integral 1 to 2 f of x dx, where in the interval 0 to 1 f of x equals pi x and in the interval 1 to 2 f of x equals pi times 2 minus x. Also we have L equals 1. After usual integration we will obtain a naught equals pi. An can be evaluated using the formula 1 by L integral 0 to 1 f of x cos pi n x dx plus integral 1 to 2 f of x cos pi n x dx, where f of x equals pi x in the range 0 to 1 and f of x equals pi times 2 minus x in the range 1 to 2. We will integrate both the integrals using integration by parts. Here we have first function as pi x, second function cos pi n x is integrated and we get sin pi n x divided by n pi. This function is differentiated with respect to x, which is written here. This function is integrated and written here. Similarly, here we will treat pi times 2 minus x as the first function and cos pi n x as the second function. Using integration by parts, we will get these terms. When you give upper and lower limit x equals 0 and x equals 1 to this term, you notice that sin n pi equals 0 for x equals 1 and sin 0 equals 0 when you give x equals 0. Similarly, when you give x equals 2 here, you will get sin 2 n pi which equals 0, and when you give x equals 1 here, it becomes sin n pi which is again 0. Therefore, these two terms involving sine function will become 0. We have only terms involving cosine terms will give non-zero answers. Here we have minus into minus becomes plus, and when you give x equals 1, we will get cos n pi divided by n square pi square multiplied to pi in the numerator, which becomes cos n pi divided by n square pi. When you give x equals 0 here, it becomes cos 0 divided by n square pi square. Along with pi appearing in the numerator, we have cos 0 equals 1 and pi by pi square becomes 1 by pi. Thus, when you give x equals 0, this term becomes minus 1 by n square pi. Similarly, when you give x equals 2 here, we will get minus cos 2n pi divided by n square pi, where cos 2n pi equals 1. When you give x equals 1, this term becomes plus cos n pi divided by n square pi. Since we have cos 2n pi equals 1, this term becomes minus of 1 by n square pi. This term is already minus 1 by n square pi. Thus we have these two terms when added will give you minus 2 by n square pi. Similarly, when you add these two terms, we will get 2 times cos n pi divided by n square pi, where cos n pi equals minus 1 the whole raised to n. Thus we have 2 times minus 1 the whole raised to n divided by n square pi obtained. You can take 2 by n square pi common from both the terms, and thus we have an equals 2 by n square pi multiplied to minus 1 the whole raised to n minus 1. We have bn equals integral 0 to 1 pi x into sin pi n x dx plus integral 1 to 2 pi times 2 minus x sin pi n x dx. Here again we will make use of integration by parts. After upper and lower limit values applied to terms after integration, we will get bn equals 0. Thus we have f of x equals pi by 2 minus 4 by pi cos pi x by 1 square plus cos 3 pi x by 3 square plus cos 5 pi x by 5 square plus etc. obtained. Giving values of a0 and an in the Fourier series representation, f of x equals a0 by 2 plus summation n ranges from 1 to infinity an cos pi nx. Inside the summation, when you give different values for n, since bn equals 0, we have only the cosine series appearing in the Fourier series expansion. Since we wish to prove this result, when you give x equals 2, in the function definition we have for x equals 2, this is the interval we have to consider, that is f of x equals f of 2 equals pi times 2 minus 2, that is at x equals 2, f of x equals 0. Thus, in the Fourier series expansion, LHS becomes 0 for x equals 2 and RHS becomes pi by 2 minus 4 by pi cos 2 pi divided by 1 square plus cos 6 pi divided by 3 square plus cos 10 pi divided by 5 square plus etc. We have cos n pi equals minus 1 the whole raised to n, and here in particular we have cos n pi equals minus 1 the whole raised to even value, because we are having for x equals 2 cosine terms obtained are cos 2 pi, cos 6 pi, cos 10 pi, etc. Values of n considered are all even. Therefore, all cosine terms become minus 1 the whole raised to even value. Thus, all the cosine terms can be equated to 1. Minus 1 the whole square equals 1. Minus 1 the whole raised to 6 equals 1. Minus 1 the whole raised to 10 equals 1, and so on. Thus, we have at x equals 2, RHS reduces to pi by 2 minus 4 by pi, 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus etc. When you take pi by 2 to LHS, it becomes minus pi by 2 equals minus 4 by pi multiplied to the series 1 by 1 square plus 1 by 3 square plus etc. When you multiply both sides of the equation using pi by 4 along with the negative sign, we will get the equation minus pi by 2 multiplied to minus pi by 4 equals this series, and we have minus pi by 2 multiplied to minus pi by 4 equals pi square by 8. Hence the result is proved.